Hi everyone again. I've got the pleasure to introduce Haoyu Ren, who's at the Technical University of Munich and also Siemens. And he's going to talk about how to manage tiny machine learning at scale and an industrial perspective. So with that, I guess we'll get started. This talk is virtual because the speaker couldn't make it here.
Hello, everyone. Welcome to my talk. I'm Haoyu from Siemens Munich, Germany. I'm a PhD candidate at Tech University of Munich. Today, I'm going to talk about how to manage tinyML at scale from our perspective. Specifically, we want to contribute a clue between the tinyML hardware and ML models. Before I start to talk about how we did that, I want to first to talk about why we want to do this. This is followed by related work. Later, we will dive deep into our approach and contributions. The proposed method and framework is then evaluated in 3 different case studies. And finally, I will conclude the talk and present our future work. There have been significant advancements in developing tinyML in the last few years. But to deploy ML models on constrained embedded devices, there is always a gap between the hardware and ML models. On the one side, various IoT devices, various embedded devices are available. They are low power, they are very cheap, and ubiquitous. However, they are also normally resources limited, and they are designed to specific tasks with different configurations, like different sensors, different memory size, and frameworks. On another side, various machine learning models have been developed to boost the intelligence of the Internet of Things. These machine learning models are normally designed with different structures, and they are often distributed as a binary file without a very clear description or understanding of their working principles. All this lead to a very fragmented IoT ecosystem. So we want to address some challenges here. How to discover an appropriate neural network, whether that neural network can run on a certain device. Vice versa, giving me a device, how can I discover which neural network or which available neural network is compatible with it? How to manage and reuse tinyML components at scale. So we propose semantic-based management of tinyML. There are already some efforts towards this direction. For example, ONNX. It is used to converting ML models across different frameworks. And there are TF-Lite, TensorFlow-Lite, metadata, model card, Autodoc. They are proposed to provide a description for each machine learning model. But here, we are less interested in converting machine learning model format. And we think manually adding a description to each model doesn't help too much regarding the reusabilities of ML models together with the embedded devices. Besides, the management of machine learning models has received increased attention in recent years, like ModelDB and Fairlets. But there still remains a gap between the IoT devices and machine learning models. Last but not least, tinyML as a service supports the deployment of ML models on versatile embedded devices. It builds abstraction layer on top of various hardware compilers. It can actually serve as a supplement to our workflow. To address the challenges that I mentioned above, we leverage semantic web technologies to achieve scaled management of tinyML. First, we introduced an ontology for describing neural network models in the context of tinyML, as shown at the left side of the figure. You can think this as a semantic schema for information model. You can think this as a semantic schema or information model for presenting neural networks. For instance, their metadata, their structures, their sensor requirement, and their hardware specifications. And besides, this information model is designed to be aligned with a thing description, or W3C TD. So TD is actually standardized to semantically describe IoT devices or embedded devices, such as their hardware specifications. With these two information models, we can basically describe tinyML components, I mean hardware and ML models, in a unified language. And our proposed framework starts by describing ML models and embedded devices against their corresponding semantic schema. Next, we centrally store the knowledge about them in a knowledge graph or graph database. With this, we make the knowledge about our models and devices searchable and manageable like web resources. And later, the developers can use various Sparkle queries to discover and reuse different tinyML components, matchmaking devices with ML models, and eventually, this allows us to deploy ML models to devices upon the matching. But at this point, you might want to say, oh, I don't know what is semantics. I have no idea what is a Sparkle query. What is a graph database? And how can I even start? No worries. We actually made the code, examples, and tutorials available in GitHub. To demonstrate the approach, we created a knowledge graph of 23 publicly available tinyML models and 6 IoT devices. And this is a very simplified illustration of the graph. As you can see, 23 ML models are shown on the left side. And one model called Move is expanded in the center. 6 embedded devices are shown on the right side of the figure. We can see that the graph database offers advantages in presenting the relationships within a complex tinyML system, especially the relationships between the devices and ML models. And with that knowledge graph created, we can actually do a lot of interesting things here using Sparkle queries. For example, the query 1, we can use it to find compatible devices given a model. As for query 2, given a device, we can find compatible models. And for the query 3, we can use it to benchmarking machine learning models for a specific task. Of course, I know these queries are not understandable for most of the tinyML developers. So we propose to integrate this system as a service into a no-code platform. And we want to hide the mechanisms from the user. And internally at Siemens, we have created a tool to search tinyML components like Google search by entering a search term here. And you can see here some filters can be applied to further refine the results. And for example, in this screenshot, after a user selected desired machine learning models, all compatible devices will be shown in a pop-up window afterwards. And we make different deployment options becomes available afterwards. So as I said, we share the code and examples in the GitHub, and we welcome any contributions. So to summarize, we supplemented tinyML with semantic web technologies. We propose a semantic information model for describing tinyML model. This semantic schema is aligned with W3C thing description, which can be used to describe embedded devices. We evaluated the method in 3 different case studies or 3 Spark queries. And we envisioned to bring the whole framework into a no-code platform to accelerate the development of tinyML. For our future work, we will keep improving our ontology towards different scenarios. We want to promote the synergy of the framework with tinyML as a service and ML ops. Of course, we will further evaluate the concept on other real-world problems. Thank you for your attention, and I look forward to your questions.
Hello, thank you so much for this interesting presentation. My name is Kautar El-Maghraib from IBM Research. So my question is about, the ontology that you're building. If somebody wants to contribute models, what's the format? Are you using Onyx, Exchange, or are you using your specific format? So how would somebody, contribute, to this knowledge graph?
Oh, thank you very much for the question. Actually, we have made all the information available on our GitHub, and I will also actually this knowledge graph or this ontology, it's basically also RDF triples, and every data is also available in our GitHub, and we also have an introduction page about this ontology, so you can overview all the detailed information in that information model.
I see. Another follow-up question. You mentioned also the connections with the model cards and these documentation frameworks.
Mm-hmm.
We also have a fact sheets framework at IBM for documenting these models. Is there a connection between what you're doing and these documentation efforts for AI models?
Yeah, I think what we want to do is to go a step further. Besides, instead of just describing the info or the information of the model itself, we want to somehow also involve hardware, somehow to create the connection between the hardware and the ML models. That's why we also choose this graph database, this ontology, because it's from our perspective of view, it's a perfect way to build these relationships between the models and IoT devices. So that we didn't, we're not only providing information about the model itself, but we also want to establish a connection to the devices, to the hardware.
I see that connection. The problem is there is no standard way of describing these models. So I just want to see if you're using a common format or.
Actually, if you have this information stored in this kind of graph database, then you can use queries directly to pull this data, and you can formalize everything. And maybe you have seen that in the video, we have actually a slide here, and we have a tool already implemented. So everything is hid behind this tool. And so user just with a few clicks and some filters and some search terms, and all this information will be retrieved directly from the graph database and displayed in a very nicely way.
Okay, thank you.
Yeah, you're welcome.
Hello, I'm Swapnil from UCLA. So my question is, right now you have this model zoo, which has, I guess, a couple of lightweight models, and you query the tool and then, give it requirements and gives you a model. So are you planning to integrate, kind of like any kind of model optimization? So, in any case, if one of these models don't fit, then, probably your toolkit can, run NAS or hyperparameter tuning and then give you a model.
Yeah, that's a great question. Actually, we started with this idea, with this management of this gap between the models and devices, and we prototyped this idea. And so our next step is kind of to extend this approach with ML ops and also tinyML as a service, that we can allow users somehow to put everything together and to maintain the model for the data collection and data monitoring, something like that. That would be in our future work. Yeah.
Thank you very much.
And we are very thankful for our sponsors. The premier sponsor this year is Edge Impulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI. NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.